Hello everyone, I'm Mr. Lee, and this is Mr. Lee's Math Class Videos. Welcome back. This is section 7.4 in Math 1316 or 2412, the trigonometric aspects. This particular one is dealing with double angle identities. This can be derived using the sum and difference formulas from the previous section. For example, cosine of 2a is really cosine of a plus a, and when you plug that into the sum of angles formula, you'll get cosine A. It's just where A and B are both A's in this case. Cosine A times cosine A minus sine A times sine A creates cosine squared A minus sine squared A. Now, because this has a cosine squared in it and a sine squared, you can convert the cosine squared using your Pythagorean identity into 1 minus sine squared A, and then combine your sines, or vice versa, combine your sine or move your sine into 1 minus cosine squared and combine the cosines. So there's really three options for cosine of 2a, depending on what's most appropriate in the moment, if you had one trig function, just the sine, you could use it to get cosine 2a, or just the cosine, or if you had both, usually if you have one, it's easy to get the other, you could do that. Sine 2a and tangent 2a don't have the same properties. They boil down to just the one equation. Sine of 2a is 2 sine a cosine a, and tangent of 2a is 2 tangent a over 1 minus tangent squared a. The primary thing when using these is to look at the relationship between the things inside. The angle here relative to the ones on the other side is double. But that also means that if you had this side already and you were going to the right side, this angle is actually half of this one. But if you start on the right side and you're going to the left, you will double the angle going the other way. So you really have to pay attention here to which side of the equation you are starting with and where you are going. We're going to start with situations that start on the right and move towards the left before we worry about doing anything going the other way. So let's get started. So simplify and evaluate the following. 2 times the sine of pi over 8 times the cosine of pi over 8. Really, you're going to look up here, and these will be on a formula chart for your quiz, so you don't need to worry about that, or you'll be allowed to use one for your quiz. So we'll have this pi over 8. We have the right side of the equation, so we have an a. So if a is pi over 8, that means when we're converting to the left side, this is really the sine of 2 times pi over 8, because it's 2a, which is really 2 times pi over 8 is 2 pi over 8, so this is the sine of pi over 4, which is the square root of 2 over 2. So you can see by how converting it can be really helpful to find and evaluate it, because we don't necessarily know pi over 8. We could, and it's not even one we could find necessarily, because it's not a 15-degree angle in any way, shape, or form, so we couldn't even use sum and difference to create it, and to have to do that twice would be much less efficient than understanding how this formula works. So it helps us extend our reach in some ways. Cosine squared of 15 degrees minus sine squared of 15 degrees. Again, this is cosine squared A minus sine squared A, which is one of our cosine of 2a formulas. So this is really cosine of 2a, where my a is 15. So the cosine of 2 times 15 is the cosine of 30 degrees, which is root 3 over 2. 2 times the tangent of pi over 12 over 1 minus tangent squared of pi over 12 is exactly this formula, where your a is pi over 12. So we've got to convert it over to tangent of 2a, so the tangent of 2 times pi over 12, which is the tangent of pi over 6, which should be the square root of 3 over 3. So as you can see, these can be pretty easy. It's really about navigating the formula. I'm going to leave D for you to practice. It's another cosine one, just in a different form, but it will work very similarly to others up there. So the question is now, what can we do with these formulas besides just answer basic questions? You might get something like find sine of 2 theta and cosine of 2 theta giving the following. Sine of theta equals 2/5 and cosine is negative. So we know, looking at the formula, that you can find cosine of 2 theta with just sine, but sine of 2a here needs both of them, which tells us we probably need the sine and the cosine of the original theta so that we can find sine of 2 theta. We have sine, and we know cosine is negative, so that's going to be second quadrant. So we draw our picture. Here's theta. Sine is 2 over 5. If we use the Pythagorean theorem, that leads the other side to be the negative square root of 21. So that should tell us the cosine of theta equals negative square root of 21 over 5. Once I have those two, I can use any of the three formulas for cosine 2 theta and use the one for sine 2 theta. So let's start with sine 2 theta. We know it's equal to 2 sine theta cosine theta. All I have to do is take these two things and plug them in. 2 times 2/5 times the negative square root of 21 over 5 equals negative 4 square roots of 21 over 25. Cosine of 2 theta, I'm going to use the original cosine squared theta minus sine squared theta since I have both of them. So that's the negative square root of 21 over 5 squared minus 2/5 squared, which should be 21 over 25 minus 4 over 25 to get 17 over 25. Now, there are some alternate ways that you could actually do this. Once you had sine of 2 theta, could you use the Pythagorean theorem? 1 minus sine squared theta gives you cosine squared theta and then take the square root? Absolutely. If you square both of these two things and add them together, they should always add to 1. I want to leave B for you to practice, so you can kind of draw the triangle and get the sine and cosine, and it'll be on the completed notes on Canvas. What else can we do with it? We can now be clever with different identities. We can do A or B. I think A is a little bit easier, so I want to leave that one for you, so we can talk through B. 1 plus tangent x times tangent 2x equals secant 2x. I'm going to start with the complicated side. So this is 1 plus tangent x, and I'm going to convert tangent of 2x using the identity into 2 tangent x over 1 minus tangent squared x. When I distribute the tangent, you get 1 plus 2 tangent squared x over 1 minus tangent squared x. Here, in order to simplify, we are going to have to get a common denominator, which means this one should be over 1 minus tangent squared x as well. So this will be 1 minus tangent squared x over 1 minus tangent squared x plus 2 tangent squared x over 1 minus tangent squared x. When we combine our numerators, minus tangent squared x is really plus 2 will be 1 plus tangent squared x over 1 minus tangent squared x. And this is where things can kind of get a little tricky, but let's see how we can deal with them. I am going to multiply this by cosine squared x over cosine squared x. What this will do when I distribute it to the ones, it'll be cosine squared x, but because tangent squared x is sine squared x over cosine squared x, the cosines will cancel, and that will leave plus sine squared x in the top. And in the numerator, it'll be cosine squared x minus sine squared x. Now the reason this is helpful is cosine squared x plus sine squared x will be 1. Cosine squared x minus sine squared x is one of our identities for cosine 2x. So this will be 1 over cosine 2x, and because it's a reciprocal, it will be able to be flipped to become secant 2x. So some of these can become longer and more difficult. A is not that way, but it does use some Pythagorean identities in order to find it. But we'll continue this in the next video.